Ladies and gentlemen, welcome back to the channel. I'm Owen with Team RECR and RE Combat Robotics. Today I am coming to you from a hotel room in Syracuse, New York. I am here on a work trip. We're doing some flight testing. Today we had a rain delay, so I got nothing better to do. I brought my film equipment out, and we're going to try to film a video today. I don't know how well it's going to go, but we'll see. I have all my equipment with me today because this Friday I will actually be going to NHRL to test out MasterBlaster, our new robot for October NHRL. Today what I want to talk about is a little bit of the design and build and decisions behind Master, which is the control robot portion of the multibot. I think it's a pretty cool design. I've got some talking points that I want to go over. Hopefully this video is going to be just a bit more casual, that I can talk about it, because I think it's really cool. So, let's jump right into it. I have Fusion pulled up on my computer here, and should be recording the screen. So, Master, like I said, is the control robot portion of this multibot. So, it's heavily focused around drive power, but it's also inspired by RAM plan. It needed to have an active weapon, so I've added a 360-degree lifter to the robot, which I'll insert some footage of us testing on screen now. The lifter is pretty powerful, but I want to go into the details of that a little bit later. Right now, I want to start out with our electronics choice, because that kind of governs everything on this bot and how it can be so small. The main thing that I was going for here is size, to keep this robot as small as possible. I think this might be one of the smallest 12s out there, especially considering, like, if you don't measure the armor, if you don't take the armor into account, because I am implementing a lot of air gap on this, which I'll talk about later on the titanium, but the base core of the robot itself is very small. Inside the robot, we're running a 1350 milliamp hour 4S LiPo. That's the weird cube-shaped battery right here. I found these off of Heli Direct, I want to say. They were scarily cheap, and I don't know how well they'll do, but this robot really doesn't pull that much amperage, so I'm not too worried about it. But the battery fits well. It fits nice in a 1.5-inch tall chassis, so I can pack everything really tight in here. From the battery, I'm running my power through a MS05 Waiachi switch. I can definitely go smaller than this, but I had some laying around from Super Scope and Cthulhu. And then I distribute power into these two bays inside the chassis. One of the sides has a Mama Max Pro sensored ESC that drives the lifter, and the other side has 4 Rhino 40 AM32 ESCs all kind of squished together into a brick. The Rhinos, I love them. They have worked flawlessly on all my testing so far, and I want to use them more going forward. 4 of them is definitely overkill for what I need, and they were quite expensive, but they seem to be really bulletproof. And they have great startup torque. I'm running sensorless drive motors, so they seem to be working perfectly. The lifter is running censored, so that's why I wanted a censored ESC. And originally I was looking at using the Castle Mama Micro X2s, because I'm only running 4S, I don't really care about the 6S rating. But I actually had 2 older Mama Max Pros laying around, because I had gotten them off of somebody from an RC car, I think. I haven't used them before. They're a little bulky, a little old. They're not waterproofed or anything else like the newer Castles are, but they're not too heavy either. So it seems like it's going to work pretty well. In my testing, I've found that it's doing nicely. It doesn't have amperage limiting, which I really like on like the Vests or the Rhinos, but it seems to be performing very well. I have done a little battle hardening on all of this stuff, and then I also am running a Spectrum AR620 receiver inside of this. I'm doing all of my mixing on my controller. I'm running a DX8E for this. So all of my drive, I'm doing tank drive, but it all has separate PWM signals. And then for the lifter, I'm currently controlling it by moving the left stick of the controller left and right to actuate the lifter. It's a little unintuitive to operate. I might change this, or if my youngest brother Corey ends up driving it, he might drive it where the drive is mixed on one stick and lifter on the other stick. Still to be determined. On my list of talking points, I also am working on a next-gen drive ESC for this. I really like the Rhino 40s, but like I said, they are pretty heavy and pretty bulky, and there's so much wiring that goes into 4 separate ESCs that they take up a ton of space. I've got a picture on screen that kind of shows like how small I was able to get it, but it's still really hard to pack into the robot, and I'd like to use the space for other things. I am working on, well, I had another individual, I commissioned them to design the board and design this ESC from scratch, which is a FOC, field oriented control ESC, that will run off of a sensor to each of my drive motors, is the intent. It'll mount on the back of the gearbox, so it should be really tight packaging. My end goal with this, I don't think it's going to be productized or anything. I want to do it just kind of as a personal project. One of my goals for a while has been to make a robot kind of without wires. And this is getting another step closer to that, where I mount the ESC onto each motor and then maybe do like a power distribution backplane or something inside the bot. I think that just the cleanliness is going to look really cool, and eventually it'll allow me to pack stuff even tighter and make the bot even smaller. The next gen drive ESC, I have some pictures of it that I can pop up on screen. Currently consists of 3 boards, a sensor board that picks up some magnets on the back of the motor, a power distribution board which handles all the MOSFETs and phases, and then a control board which has the logic on it. And then it's just supply power and supply PWM, just like any other ESC that we're using in these robots. And I should work pretty good. I am in process right now of trying to get that through PCBWay ordered for my prototypes, and that should be later this year. It's not going to be at the October event because it's just a long-term project, but should be something really cool. Lifter-wise, I'll probably stick with a Castle or maybe a Vesk in the future. I really like those. Next, we'll jump into probably the most important thing on this robot, which is the drive. As a control bot, if you can drive well, if you can push well, if you have the speed and maneuverability to run around the box, you're going to do pretty well. Even if you don't have the most powerful lifter, even if your armor config isn't the best, if you can outdrive your opponent, you can win a lot of matches that way. I'm going off of other experience. I have not built a control bot before. Most of my stuff is glass cannons. But I have taken what I've learned on previous bots and kind of baked it into this one. This robot uses 4 Tempest 2808 1000 kV motors for drive, 1 per side. There's no belts or anything. It's all independent. I kind of went down that road because I wanted redundancy. It's not the best if you are pushing somebody and you like weigh down your front wheels more than your back wheels. So in the future, I might look at putting a belt in between the two to help with power transfer. Not necessarily for like that I need a belt or a track or anything, but if you bog down one set of wheels, the other wheels could transfer. With tires on the bot, it's not that big of a concern because you'd break the tires free, but I am planning on running cleats. I'll put some pictures up on screen. I have 2 different options. I want to run the cleats. I think it's going to perform better. It's performed better in my testing. We'll see how it does in the actual cage. But yeah. But each of those motors is paired with a very customized single-stage BaneBots gearbox that is a 4-to-1 reduction. And I've actually added another planetary gear in there, so it's got 5 planets. The idea there is just to distribute more force. That is getting plumbed into a custom titanium drive axle. Those are made by our team sponsor, Triangle Precision Industries. Those titanium drive axles then go to a cool flange drive mount that I've designed. What this is a 1/4-inch plate of 7075 aluminum that I had send cut, and then I tapped after receiving it. It is only, like I said, only a 1/4-inch thick. It bolts to the axle with the end tap, and I insert shims and tighten everything up. If I pull up the section view here and zoom in on one of the drive pods, over here we can see the Tempest motor. This is the CAD from Innovative Designs. Here's my mount, and then I have my pinion on my motor. This is where the planets would sit in this area right here. You can see the ring gear on the outside, and then here's the axle shaft and flange. I am running 12mm bearings and axle shafts, the same as what the older Goldie boxes ran that I sold. And then it's an 11mm Rex shaft, the same FRC one on the output. So then the 1/4-inch plate bolts onto that. These pieces right here are the shims. These are 1mm aluminum shims that slide over the axle so that when you tighten this end bolt, there's like a 10 thou gap right here that allows the plate to be taken up. When you tighten that end bolt, it actually tightens against the inner races of the bearings and pulls everything together. So you're preloading your system so you don't have that classic slop that these gearboxes like to have. Because when you tighten everything up, there's no gap for the snap ring or anything else to move. So your wheel is a lot more rigidly supported, And if the wheel gets hit from the outside, you're not driving the axle into the robot. The older style Banebot stuff, you could pull the axle out because the snap ring would pop off. The newer style kits, like the Goldie Box conversions were, or that the Repeat Magnums were, are a lot beefier, and you can't pull the axle out because it's all a billet shaft design. But if you get hit really hard in the wheel, you can still pop the snap ring off and shove the axle inwards, which I've had on Super Scope before. Take the Planet gears and shove them into this aluminum plate here and actually imprint them on it and cause some binding and some debris. The goal of this was to decrease the risk of debris, so that everything would roll a little bit more free and that you're not going to gall up a gear because there's a burr in there. The other thing I've done to prevent that is I designed this step inside the axle. Let me see if I can open that up real quick. The step inside the axle on the inside is something new that I don't think I've seen people do before. You really can't do it on if you were doing multiple different stages. Like if you had a 2-stage gearbox, it wouldn't work like that. But on a single-stage gearbox, since there's no sun gear in the middle stage, and I'm pressing the sun onto the motor shaft here, I left the gear. Normally you have to cut the gear down short, and you have to cut the axle short for it to all fit inside. Adding this step here means that I can just take a motor off the shelf, bolt it to a plate, press this gear on, and I don't have to cut it down. And I've seen before that when you cut the gears down, you cut the shafts down, you can get them crooked on there, you can have some burrs introduced in there, and those sharp edges of that gear, and you're also not getting 100% mating contact. Those burrs can come off during matches and mulch up your gearbox and get damaged. So this gives me 100% contact with my Planet gears and no risk of debris. The debris was a major thing that I've learned previously that I'm trying to reduce. Plus, it makes the axle a little bit lighter, which is always nice. You can see I've had my end tap go a little bit deeper in here so that I'm trying to remove as much material out of these axles as I can to make them nice and light. The last thing on my talking point for these gearboxes is the integration into the frame. I've done this on a lot of my bots previously. Razor's Edge did it with its 3/4 inch thick drive rails. It ran integrated P6s. This bot does it as well. Here I can pull up this side frame, and the side frame just has bearing pockets on both sides, and it has the pin receiving holes for the gearbox. So these holes get pins pressed in them. I think they're 2mm dowel pins that prevent the gear from rotating, and then the 12mm ID bearings get pressed into either side of the frame rail. This allows me to totally get rid of the front of the gearbox so it can be integrated into the frame, and you can see how nice and compact this makes it. Like I said, I've done this on a lot of bots in the past. I think it's a good way to go. I did learn on Razor's Edge, I put Razor's Edge ran 1/2-inch axle shafts because I was worried that they would get hit. When you run too big an axle shaft and you put a big bearing in there, like it ran 2 R8 bearings per side, if your frame isn't thick enough, the bearing gets too close to the wall. And I actually took a hit from above from Bigish, and it didn't go through my top plate, but it crushed it down enough because there wasn't much support material in that area, that it caused my drive to get a little bit bound up. So if you are running bigger bearings, you need to put a lot more meat around the side frame, because even though it's structurally sound, you can crush that aluminum in there and the bearing can get damaged. So this one is running the normal 12mm ID bearings, so it's got enough meat around there that's not a problem. Also on my talking points for this is the drive speed. This bot is geared at 30 miles an hour for top speed, which is really high, especially if you're familiar with 3-pound bots. They might be geared almost for like 6 to 9 miles an hour because the cage is smaller. In the 12-pound class, I want to say the most common speed is like 16 to 18 miles an hour, and that's still pretty quick. Super Scope has been geared really high for a while, and I've been experimenting with low reduction drive systems. Actually Seth just released through Just Cause Robotics a low reduction drive system for 3s, where you only have a single stage gearbox. And the main benefit of this is when the bot goes flying across the arena or the wheel gets hit, you don't have that high back driving force that you would normally on a 2 or 3 stage gearbox. And this is why a lot of people prefer belts or tangent drive. It's the same idea. That the lower reduction you have, the easier you can to back drive your motor. So if the wheel gets hit, it can just rotate instead of it shearing gears or getting damaged or anything else. That's why you'll see bots with high reduction drives get their gearboxes damaged more often, is because of that reason. where it's when you hit the wheel fast, it's going to shear stuff off. So this bot, Master, runs 4-to-1 reduction on each drive side. Razor's Edge, the most recent version, I tested 5-to-1 reduction. Superscope was 4-to-1. No, Superscope was 5-to-1. Marrow was 5-to-1. This one's 4-to-1, but I'm also running way smaller wheels and a lower voltage battery, so it seems to be working pretty well. Even though I'm geared really high on drive speed compared to some other bots out there, I haven't found it being an issue in testing so far. We're going to see how bad the bot digs in and bogs on the test floor at NHRL, but on the chipboard that I've been using to test on, it'll still break the tires free and cut grooves in the floor, even at this high of gearing. That's just how nice these Rhino 40s are. Alright, with all that boring drive stuff covered and electronics, we can jump to the lifter, which is one of the cooler parts of this bot. The lifter on this is a brushless lifter, which there's a lot of them in the 3-pound class, but in the 12-pound class, there's not too many. Ramplan ran a brushed lifter, which was a brushed RS550 with a 132-to-1, I believe, 3-stage Bainbots gearbox. I am running a brushless Neo 550 motor. I chose that because it's censored off the shelf and nice and small. It's about the only thing that was censored that I didn't have to add on to in this size, and I had a couple of them laying around for testing. And then I have a 104-to-1 reduction Bainbots gearbox, which is 2 5-to-1 stages and a 4-to-1 output stage. One of Ramplan's main drawbacks that I had researched into was the output stage of the gearbox getting cut, the pins shearing off. And that's why I went with the 4-to-1 reduction on the output stage, because those gears are a lot stronger, and the main thing that would happen would be that the pins would shear or the sun gear would break. So I changed that, was one of the main things, and then I have added a clutch. Inside this model, it actually isn't the right clutch because I've been playing around with a lot of different ideas. The clutch that I ended up going with was kind of a backup option. I wanted to try, and I actually machined a mechanical clutch that would break over with gear force, and it didn't end up working very well. And the main reason for that was the friction between the spline that I was trying to do. The clutch essentially has to transmit torque and be able to slide at the same time, and it wasn't working very well. This new one that I created uses like a socket and inner piece. I'll actually isolate this for a second. So it essentially looks like just a wavy shaft socket on the inside and outside. And I'll put some pictures on screen of these in person as well. Both of these parts are S7 tool steel made by Triangle Precision Industries. And the center piece on here is a printed piece of TPU with hollow insides. The idea with this is that you can take the TPU and it'll transmit torque just like a normal shock coupler as usual, but then the walls can compress here. So you have your two outside pieces, and when it tries to roll through the tight gaps, it'll compress and go flat. And my idea was, okay, as a backup, we can always put this in there if the mechanical clutch didn't work. I can print it solid and it'll just act like a spider coupler. Or if this does work, I can print it with these low walls and it'll work. The idea is that I could adjust it, like adjust 95 or 98 TPU and how many walls I want to do and adjust it. And on the very first try of printing it, I got it dialed in exactly where I want. I was able to get 25 foot-pounds out of this, where the bot will run the lifter arm all around, no problem. But if you put over 25 foot-pounds on it or hit it fast, it'll break over, which is perfect, which is exactly what I want. I haven't seen something like this design before. I've seen some mechanical things like on Sawblaze and Megatron implemented before. But this design I haven't seen I don't think I've seen one in a combat robot before, and I really like it. So if I build more lifters in the future, I'm definitely going to put this on there because it hasn't been combat tested yet, but I think this is what's going to save my lifter compared to others, so I can actually get the arm hit and back driven and it not wreck my gearbox. Speaking of the arm is a piece of 3/16 titanium that we had water jet cut by Triangle Precision Industries. It's about 9 inches long, I want to say. The bot's really small compared to something like Ramplan. I want to say Ramplan's like 13 inches, maybe a little bit more than a foot. So I've got a bit shorter of an arm on here, and I also have shock mounted it with the same idea of how I mount the cleats or tires. You bolt to the same flange of the flange drive axle, and it gives it a little bit more shock mounting on the arm. I'm not relying on that to save the gearbox. I'm relying on the clutch inside the arm to save it. The arm can move a full 360 degrees around the bot. There's no limits, anything else. It's all just controlled by hand. And I have the motor set to coast right now, with the idea being that I can kind of float the arm on the ground and it'll ride and ground scrape. If I turn braking on, then I would have to like exactly position it, which I don't want to do. I want to be able to just kind of tap the stick and it float to the ground so I can use it as a fork or lift people up when I want to. And it seems to be working well so far. I'll put some pictures of videos of me testing this at NHRL, seeing how it works. But I'm excited to see how it performs. This is going to be something that I think is pretty cool, and it's going to give me a lot of versatility inside the arena. Lastly, we have the actual frame and armor that goes around the spot, what holds it all together. In the CAD, what you're seeing here, all of the orange anodized parts, these are all 6061 aluminum. Probably could have done 7075, but I'm familiar with how 6061 performs in this application. I'd rather it get a little mangled up than crack at like a tight point or something. What I am doing to protect the frame from these heavy hits is I have these 3D printed bushings, which go in all of my holes. The front and rear of this bot has different bushing styles. The rear bushings are double pin, so it can be stationary, and the front bushings are single pin, so it can hinge. So I can have a hinged front plow on here. These bushings are currently printed out of 95A TPU. They're like a 16th inch wall. They are designed to be wear components, where if the plow gets hit, it's going to wear and bang on these TPU pieces and not damage my nice frame underneath. The actual pieces that'll interface with it are these big welded titanium assemblies. The pictures that I'm going to throw up on screen now probably aren't the finished versions. We're probably going to do a little bit more welding on them, but it's what we were able to put together in time for the NHRL test. The front one is 3/16 titanium, bent and welded with 3/16 flanges. The rear has 3/16 flanges and a 90 thou outer shell. The idea being the rear doesn't need as much armor as the front. I'm primarily going to always put my front at people. And the pins that hold these on, the rear one has a bunch of 1/4 inch aluminum pins, and the front one has some 3/8 inch aluminum pins. The idea being here that there's just a quick cotter pin that you can pull and remove the plow and service it. So every time it comes out of a match, you pull the pins, pull the plows off of it, and you can work on those or have another teammate work on those separately in the pits. The front of the bot also features the carbon fiber forks. I'm a big fan of the carbon fiber. They'll shatter when they get hit really hard and not bend out into your way, and they're super lightweight. So these are 6mm carbon fiber forks. They come out about as long as the arm. I think they stick out like 3.5, 4 inches from the bot, and they pivot on the same point that the plow does, but they're actually independently hinged. So the plow can ride over bumps, and the forks will glide along the ground, hopefully always staying underneath people. Both of these also have travel limits, so if they get hit in a weird position or if I get flipped over, I'm not going to get stuck in those positions, hopefully. The rear armor also has some fancy 3D printed stainless pieces, which I will insert pictures of on screen now. These were done by PCBWay. They were only like $6 a piece, although I did have to drill and tap them when they got back from being printed. And these hold some little wires out the back, which I'll talk a little bit more about in the video about Blaster. Well, this is the first time I'm using 3D printed metal on a robot. This was a cool opportunity for me to try to do. If they don't work or they break pretty often, we'll probably have some aluminum backups that we can try instead. But they look extremely cool, and I also used Fusion's generative design tool to make these. So it's just a really cool part in general that I want to experiment more with. Lastly, on the frame, we've got some standard carbon fiber covers. These are 3mm thick, made by CNC Madness. They pocket in on the top and bottom of the bot, hold the whole thing together, and all bolt in place. Pretty simple in that regard. So that should be pretty much all about Master. It's a straightforward bot compared to what I normally build. My first type of control bot, first bot without a big active weapon on it, like a spinner. And I'm excited to see how it goes. This project was started a little while ago, and I wanted to give myself more time on this. And I think I've done that pretty well. I've actually been able to drive and test this bot pretty extensively, play around with the clutch, iterate on some things, and being able to head out to NHRL early and test in the cage, I think is going to give me a ton of drive experience and everything going into this October event. I think it's going to be pretty cool. We still have to do the stickers for Master, still had to come up with some paint schemes. We got to do a little bit more testing and programming on all the ESCs, part of what I'm going to try at the event. And then we got to do some finish welding on all the plows. But other than that, it's looking pretty good. I'm excited to see it come together, and we'll probably put out some more shorts or videos on Master itself and some performance. in addition to all the videos that I've inserted inside this video. I'm not sure if I'm going to publish this video separately or if this will get lumped in with another video about Blaster. Might split them apart into 2 pieces. But that's about all I have for today. We'll see how this video turns out, how it's received. I want to do something a little bit more casual. Normally I spend a lot of time worrying about audio and scripts, and that today was just off the cuff. I like talking about robots. What can I say? So if you like the video, make sure to give it a like. Helps me out. And I will see you hopefully pretty soon with another video. Not as bad an upload schedule as previously. So thanks.